Explore groundbreaking construction feats, tunnel breakthroughs, and massive pipeline installations that redefine engineering limits, scale, precision, and human ambition worldwide today, together. Inside the tunnel, the excavation cycle follows a strict and repeatable sequence to ensure stability and safety after each advance. First, once a section of rock has been exposed, workers begin installing the supporting mesh. Steel reinforcement mesh is positioned tightly against the tunnel walls and crown. This mesh provides immediate surface support, preventing loose rock fragments from falling and creating a stable base for the next support layer. Next, crews move on to applying the shotcrete. A concrete mixture is sprayed at high pressure onto the rock surface, fully embedding the steel mesh. This shotcrete layer bonds with the rock, sealing cracks, reducing deformation, and forming a continuous protective shell. It allows the tunnel profile to be secured quickly before deeper reinforcement work starts. After the shotcrete has set sufficiently, operators start drilling for the securing anchors. Using drilling rigs, holes are precisely drilled into the rock mass at predetermined angles and depths. These holes are designed to accept rock bolts or anchors that will tie unstable outer rock layers to the stronger rock deeper inside the mountain. The next step involves introducing the securing anchors. Steel anchors are inserted into the drilled holes and fixed in place, usually with grout. Once tensioned, these anchors actively stabilize the surrounding rock, limiting movement and improving long-term tunnel stability. With the tunnel temporarily supported, attention turns back to excavation. Crews begin drilling the blasting holes at the tunnel face. The drilling pattern is carefully calculated to control the direction and size of the rock breakage. Each hole is positioned to ensure efficient fragmentation while minimizing overbreak. Then comes preparing for the blast. The face is inspected, drilled holes are cleaned, and safety checks are carried out. All unnecessary equipment and personnel are cleared from the area to maintain strict safety conditions. After preparation, workers proceed with filling the holes with a two-component explosive. This type of explosive is stable during handling and only becomes active once mixed inside the boreholes, making it suitable for tunnel environments. Finally, crews focus on connecting the detonating fuses. The fuses link all charged holes into a single blasting system, ensuring precise timing and controlled detonation. Once connected and checked, the area is evacuated, and the blast is initiated, breaking the rock and allowing the tunnel to advance for the next cycle. After approximately 555 days of continuous operation and tunneling through over 200 meters of rock, the tunnel boring machine reached Kokam on November 7, 2011, around noon. As the machine approached, rumbling sounds echoed through the mountain, signaling its arrival. The reinforced shotcrete wall at the tunnel face began to crumble progressively. Shortly after, the rotating cutter head of the TBM broke through the remaining wall, marking the successful breakthrough. Dust and debris scattered as the machine emerged from the mountain. Workers observed the process closely and began clearing the tunnel face. The Heron Connect tunnel boring machine played a decisive role in the breakthrough of the Belchen tunnel near Basel, marking an important milestone in modern tunneling technology. On June 21, 2017, the 200-meter-long tunnel was successfully cut through when the massive TBM emerged on the opposite side of the Jura Mountains after only 72 weeks of excavation. With a cutting head measuring almost 14 meters in diameter, the Heron Connect TBM was designed to handle hard rock conditions with high precision and reliability. As it advanced underground, the machine simultaneously excavated the rock face, transported spoil away from the tunnel, and supported the newly excavated section to ensure stability and safety. This integrated working method allowed continuous progress while maintaining strict control over alignment and tunnel geometry. The breakthrough was not only a technical achievement, but also a symbolic moment. Inside the machine, a small statue of St. Barbara, the traditional patron saint of miners and tunnel workers, accompanied the crew throughout the drive. Her presence reflected long-standing tunneling traditions and the respect for safety in underground construction. Overall, the Belgian tunnel breakthrough demonstrated the efficiency, power, and engineering excellence of Heron Connect TBMs, confirming their key role in delivering large-scale tunnel projects in challenging geological environments. The TBM breakthrough project on Mumbai Metro Line 3 marks a significant milestone in underground construction. The tunnel boring machine Godavari 3 successfully completed the downstream tunnel section connecting BKC to Vidyanagari and Tarabi. Over a distance of approximately 890 to 500 meters, the TBM advanced steadily through complex urban geology beneath one of Mumbai's busiest areas. During excavation, the machine continuously cut through soil and rock while installing precast concrete lining segments to stabilize the tunnel. Precise monitoring ensured alignment, safety, and minimal surface disturbance. The breakthrough moment represents the completion of this tunnel drive and confirms the effectiveness of mechanized tunneling for large metro projects. This achievement contributes to the timely progress of Mumbai Metro Line 3 and strengthens the city's underground transport infrastructure. This achievement contributes to the timely progress of Mumbai Metro Line 3 and strengthens the city's underground transport infrastructure. At the tunnel face, the carrier lifts the folded tubular steel rib into position. The rib is then opened automatically. During this phase, the central arm of the handler positions the main tubular section of the steel rib, while the two side arms simultaneously handle the paired side sections. Because the bracing elements between each tubular steel rib are pre-installed at the factory, no on-site assembly of bracing is required. Next, the handler pulls the newly positioned tubular steel rib toward the previously installed rib. This controlled movement engages the pre-installed bracing elements, which automatically lock the adjacent ribs together at the designed spacing. After the ribs are connected, each foot of the tubular steel rib is carefully positioned at ground level to ensure correct alignment and load transfer. To enhance the structural resistance of the support system, the tubular steel ribs are subsequently filled with concrete. This operation completes the primary support installation, providing stiffness and long-term stability to the tunnel lining. Throughout the entire procedure, no workers are required to be present near the tunnel face during installation. The semi-automatic system eliminates the need for manual handling, assembly of sections, or positioning of bracing and feet. As a result, hazards such as falls from height, limited visibility, and exposure to continuous construction noise are significantly reduced. The process ensures a safe, precise, and time-efficient installation of the B0 Tondo primary tunnel support system. The drilling process shows how a new crosscut is developed perpendicular to an existing underground drift using a highly automated jumbo drill. To begin with, the Sandvik DD422i is positioned inside the confined underground heading and aligned for a 90-degree crosscut. Thanks to its compact design and articulated carrier, the machine can be accurately set up even where space is limited. For this type of operation, the jumbo is equipped with TFX telescopic feeds, which allow the use of both long and short drill rods. This flexibility is essential when drilling sideways holes, often referred to as sidewinders, where a full-length fixed feed cannot be accommodated. Once in position, the operator uses the Sika intelligent control system to plan the drilling pattern. The system calculates a precise reference plane based on X, Y, and Z coordinates, ensuring that the new heading is drilled perfectly perpendicular to the main tunnel. Automated navigation assists the operator in maintaining correct hole alignment, spacing, and depth throughout the cycle. The SB60 or SB60i drilling booms then come into operation. With hydraulic parallel hold and high maneuverability, the booms can reach extreme angles required for establishing the initial cut, such as a V-cut or burn cut, which is critical for opening a new 90-degree heading. The booms accurately position the rock drills, and drilling proceeds in a consistent and repetitive sequence, as shown in the time-lapse. In addition, the optional dual controls package allows a single operator to switch seamlessly between drilling and ground support tasks. After completing the face drilling, the same machine can immediately perform bolting and mesh installation, improving efficiency and reducing downtime. Overall, the process demonstrates how the Sandvik DD422i combines precision drilling, automation, and versatility to safely and efficiently create 90-degree underground mine headings. The Epiroc Cabletech series represents a fully mechanized solution for cable bolting, specifically developed for underground mining and tunneling operations, where safety, accuracy, and productivity are critical. The Cabletech machines are designed to carry out the complete cable bolting cycle in a single, integrated process. This includes drilling, grout mixing, grout pumping, and cable insertion, all performed under controlled and automated conditions. Among the range, Cabletech E is the largest model, making it well-suited for medium to large tunnel profiles and demanding underground environments. In terms of onboard capacity, Cabletech E can store up to 1,000 kg of dry cement and approximately 1,700 meters of cable, allowing long operating cycles with minimal interruptions for reloading. The machine is capable of fully mechanized drilling to depths of up to 32 meters, which also enables it to function as a supplementary production drilling unit when required. A key advantage of the Cabletech series is its full mechanization, which keeps operators protected inside a certified FOPS-approved cabin or under a protective canopy, significantly reducing exposure to unsupported ground. Quality control is ensured through an automatic grout mixing system that follows preset ratios and continuously logs operational data for later analysis, guaranteeing consistent rock reinforcement performance. Productivity is further enhanced by the dual boom design, allowing two tasks to be carried out simultaneously and reducing overall installation cycle times. Operation and monitoring are managed via an intuitive touchscreen control system, offering diagnostics, data recording, and efficient machine management. After blasting and ventilation, fragmented rock and broken material are first removed using the Sandvik LH203 LHD loader. This machine enters the heading to muck out loose rock, loading and hauling it away from the face to keep the tunnel clean and accessible for the next operations. Continuous mucking ensures that the excavation area is fully cleared and safe for support installation. Once mucking is completed, ground support operations begin. The Sandvik LH207, equipped with a scissor lift platform and stabilizing outriggers, is positioned under the excavation roof. From the elevated and secured platform, roof bolts are drilled and installed to reinforce the freshly blasted rock surfaces. This step provides immediate support and prevents loose rock from falling. At the same time, a Mechanized bolting machine is used to install vertical pillar bolts. These bolts strengthen load-bearing rock zones and improve the overall stability of the tunnel structure, especially in areas subjected to high stress. After primary bolting is completed, the Sandvik DS411 is deployed to carry out additional drilling and installation tasks. This machine drills precise holes and installs further support elements where required, preparing the heading for the next excavation cycle. Finally, the Sandvik DD311 jumbo drill is brought to the face to drill a new round of blast holes. Accurate drilling patterns are created to ensure controlled blasting, allowing the mining cycle of drilling, blasting, mucking, and ground support to continue efficiently. The jumbo drilling machine drives into the tunnel and stabilizes itself using hydraulic jacks. Its hydraulic booms are then carefully aligned toward the tunnel face. Technicians, sometimes operating remotely, guide the drilling arms to follow a precise drilling pattern. Powerful, rotary percussive hydraulic drills penetrate the rock to create blast holes, rock bolt holes, and drainage holes. Automated control systems continuously adjust positioning, depth, and angle to ensure accuracy and safety. Once drilling is completed, the area is prepared for blasting. After each blast, broken rock is removed, the tunnel face is secured, and support systems are installed. This drilling, blasting, mucking, and support cycle is repeated to advance the tunnel efficiently and safely. The HDPE double-wall corrugated pipe extrusion line is a high-performance production system designed to manufacture durable pipes with a corrugated outer wall and a smooth inner layer. Using dual single-screw extruders, the line simultaneously processes the inner and outer layers, allowing different materials or colors. A co-extrusion die head ensures uniform wall thickness, while the corrugator shapes the outer profile using vacuum or pressure forming. Controlled by a PLC system, the line delivers precise, automated operation for producing pipes used in drainage, sewerage, and underground cable protection. The welding of a 42-inch pipeline using the Lone Star automated welding system This system applies a single-head GMAW process to complete the cat pass with high precision and consistency. Welding is performed downhill inside a narrow groove, allowing better control of heat input and weld penetration. The automated setup ensures a stable arc, uniform bead appearance, and reduced human error compared to manual welding. By combining mechanized travel with controlled parameters, the Lone Star system improves productivity, weld quality, and repeatability, making it well-suited for large-diameter pipeline construction projects. The CRC Evans copper backup clamp, commonly referred to as the CBUC, is a highly specialized electromechanical and pneumatic unit designed to support pipeline welding operations. Its primary function is to securely clamp the pipe in position while simultaneously providing a copper backing surface for the external root weld pass. By stabilizing the pipe joint and ensuring consistent weld quality, the clamp plays a critical role in achieving precise alignment, strong weld penetration, and efficient joint-to-joint production in pipeline construction. At its core, the copper backup clamp combines electrical power, pneumatic force, and remote-controlled operation into a single self-contained system. This integrated design allows the clamp to operate reliably inside the pipe while maintaining full control from the outside, significantly improving both safety and productivity on the job site. The electrical system of the copper backup clamp is a self-contained 24-volt system. This system supplies power to the radio frequency transmitter, as well as the air control valves that regulate pneumatic functions. The main components of the electrical system include a voltage meter, an Anderson plug mounted on the nose cone for charging and power connection, and two 12-volt batteries located at the rear of the clamp. Together, these components ensure stable power delivery during operation. The voltage meter allows operators to monitor battery condition, while the Anderson plug provides a convenient and secure charging interface. Because the system is fully self-contained, the clamp can operate independently inside the pipeline without relying on external power sources during welding activities. The pneumatic system is essential to the operation of the clamp. All major mechanical functions, including the clamping shoes, drive wheels, and braking system, are powered by compressed air. The primary components of the pneumatic system consist of a nose cone quick disconnect fitting, pressure gauges, an oil fog lubrication system, and two air tanks mounted at the rear of the clamp. The smaller air tank supplies pressure to the brakes and clamping mechanisms, ensuring secure pipe holding during welding. The larger air tank, which can be pressurized up to 210 psi, provides the force required to drive the side-mounted wheels. These drive wheels press against the internal pipe wall, allowing the clamp to move smoothly from one joint to the next. The travel speed between joints is adjustable, giving operators precise control over clamp positioning. The copper backup clamp is operated using a radio frequency remote control system. With this remote, the operator can control a wide range of actions, including raising and lowering the clamping shoes, engaging or releasing the brakes, driving the clamp forward or in reverse, and initiating automatic travel between pipe joints. To begin operation, both the RF receiver on the clamp and the remote control must be powered on. A flickering indicator light on both the receiver and the remote confirms that a secure link has been established. Once connected, the operator gains full control of the clamp's functions from outside the pipe, reducing the need for manual intervention and enhancing overall safety. Before inserting the clamp into the pipe, it is important to inspect the oil fog lubrication system. Located beneath the batteries at the rear of the clamp, the oil fog reservoir introduces a controlled amount of lubricant into the pneumatic system. This lubrication minimizes wear on internal components and ensures smooth, reliable operation. The oil flow rate can be adjusted using the screw located on top of a glass dome. The recommended setting is approximately 6 drops per minute. The oil fog is visible whenever pneumatic functions are activated, providing a clear visual confirmation that lubrication is being delivered correctly. The idler wheel assemblies, located beneath the clamping shoes, must be properly adjusted to ensure the clamp remains centered within the pipe. Correct alignment is critical for consistent copper backup positioning and stable clamp movement. To check the adjustment, the rear shoes are raised while observing the center of the nose cone. If the nose cone remains centered, the idler wheel assemblies are correctly configured. If horizontal movement is observed, the idler wheel spring assemblies require adjustment. This process involves moving the clamp partially out of the pipe, inserting the red safety peg behind the shoes, loosening the spring assembly nut, adjusting the spring height, and retightening the nut. Adjustments are repeated until the nose cone remains centered during shoe activation. To install the clamp, it is lifted using the designated lifting arm. A safety pin must be inserted through the lifting beam to restrain the clevis. The clamp is guided into the pipe rear end first until the clevis contacts the pipe end. Before insertion, the brakes should be retracted. Once the clamp is inside the pipe, the drive wheels are raised and the unit is jogged forward until the idler wheels are fully inside. The clevis is then unhooked and tucked inside the pipe behind the clamping section. With air pressure applied, the clamp is ready for full operation. The copper backup clamp performs 2 primary functions: aligning the pipe ends and providing copper backup for the external root weld pass. The operational process consists of 4 main steps. First, the clamp is positioned so the copper shoes align precisely with the pipe bevel edge. Second, the pipe ends are aligned by bringing the next pipe section into position. Third, the front and rear shoes are raised to clamp the joint securely while welding is performed. The copper shoes provide a smooth backing surface, ensuring proper weld penetration and bead formation. Finally, once welding is complete, the clamp automatically travels to the next joint, where the process is repeated. To maintain optimal performance, periodic inspections of the clamp are essential. Operators should check for air leaks, worn components, loose connections, and proper lubrication. Copper shoes should be replaced when they become excessively pitted or worn. Replacement involves raising the copper shoes, removing the fasteners, installing a new shoe, and securely retightening the fasteners. In summary, the CRC Evans copper backup clamp is a robust and highly efficient tool for pipeline welding operations. Powered by a self-contained 24-volt electrical system and a reliable pneumatic network, it provides precise pipe alignment, secure clamping, and high-quality copper backup for weld passes. At a depth of 140 feet, experienced divers carry out a subsea spool installation project. The work involves removing old pipe sections, measuring replacements, and installing prefabricated steel spools. Hydraulic bolt tensioners and torque tools ensure precise flange bolt tightening, following strict torque sequences. The pipeline construction process begins with individual steel pipes positioned along the right-of-way. These pipes typically measure between 24 and 48 inches in diameter, and the selected diameter directly determines whether hand welding or automatic welding methods are used. Once delivered, each pipe is carefully set on timber cribs to stabilize it and raise it off the ground, ensuring proper access and alignment for subsequent operations. Before welding begins, crew members preheat the steel pipe within a specified temperature range. This controlled preheating is critical, as it reduces thermal stress and prepares the material for strong, defect-free welds. In areas where terrain prevents straight pipe placement, journeyman pipe layers and laborers use cold bending machines. These machines form precise bends in the pipe, allowing it to follow the natural contours of the land while maintaining structural integrity. For final alignment, a pipe layer known as a stabber guides a side boom operator as two pipe sections are carefully brought together. Once the pipes are squared and aligned, a clamper secures heavy-duty clamps around the joint to hold both sections steady. This stabilization is essential before multiple welding passes can be performed. In automatic welding, the first pass, called the bead weld, is completed by a welder operating remote controls from the open end of the pipe. This is followed by several fill welds and a final cap weld. Together, these weld passes create a permanent, high-strength joint designed to last for the entire service life of the pipeline. Each completed weld pass is marked with an identifying control number, allowing inspectors to trace workmanship and verify quality. For hand welding, teams of two welders often work together using a downhand welding technique specific to pipeline construction. Experienced welders may supervise junior crew members, ensuring skill transfer and consistent quality. Beyond standard welding, pipe layers and welders also complete tie-ins, which connect finished pipeline sections to other parts of the system. Welding and pipe laying operations ultimately set the pace for the entire pipeline construction process, making precision, efficiency, and coordination essential at every stage. In large-diameter Canadian mainline oil pipeline projects, construction craft labor plays a vital role from the earliest stages through to final restoration. These careers involve hands-on technical work that supports every phase of pipeline construction and requires a strong understanding of safety, precision, and teamwork. At the start of a project, labor crews are responsible for clearing the right-of-way, which is the narrow corridor where the pipeline will be built. In forested areas, this work must follow land survey markings, forest management practices, and strict safety procedures. Laborers ensure operations comply with environmental regulations and respect both private and public land. In populated areas, workers build quality fencing to secure the construction zone and protect landowners and crews. During winter construction, snow fences are installed to control drifting snow and maintain safe working conditions. As the pipeline spread progresses, individual pipe sections weighing several tons are delivered, unloaded, and stockpiled. Construction craft workers use specialized slings and hooks to prevent damage to the pipe coating. They then work closely with truck drivers and equipment operators to reload and position the pipe along the right-of-way, a process known as stringing. Skilled setup crews place each pipe section precisely according to engineering plans, especially where terrain curvature requires pipe bending. Laborers also assist journeyman pipe layers in operating bending machines and organizing wooden skids and skid piles to safely support the pipe before welding. After welding, other specialized crews inspect weld integrity using advanced inspection technologies. Sandblasting teams clean the weld areas, while induction heating operators reheat the pipe so applicator crews can apply a seamless protective coating. Final inspections identify coating defects, which are repaired and retested. GPS technology is used to record the exact location of every weld before the pipeline is lowered and backfilled with topsoil. Across all these stages, construction craft labor careers demand adaptability, technical skill, and continuous learning, making them essential to the efficiency, safety, and environmental responsibility of Canada's pipeline industry. Precision Pipeline is positioned as a next-generation pipeline contractor, combining proven industry experience with modern construction practices. Building on decades of field knowledge, the company delivers high-quality pipeline installation services while embracing innovation, efficiency, and safety. Precision Pipeline focuses on executing complex projects with advanced equipment, skilled crews, and streamlined workflows that improve productivity and consistency in the field. By integrating traditional craftsmanship with new technologies, the company is able to meet the evolving demands of large-scale energy infrastructure. Emphasis is placed on precise planning, accurate execution, and strict quality control at every stage of construction. Safety and environmental responsibility are treated as core values, guiding daily operations and long-term decision-making. As the pipeline industry continues to evolve, Precision Pipeline represents a forward-looking approach, delivering reliable results while setting higher standards for performance, professionalism, and sustainability. Through this balance of experience and innovation, the company defines what a modern pipeline contractor should be. Real-time radiography is revolutionizing pipeline inspection by delivering faster, safer, and more efficient weld evaluation. The process begins by preparing and installing pipe bands around each weld, onto which the RTR unit is mounted and remotely controlled. TechCore provides two inspection methods: a battery-powered internal X-ray crawler that travels weld to weld inside the pipe, or a double wall technique using an externally installed X-ray tube connected to a power source. The weld scanner is mounted on claws and linked wirelessly via Wi-Fi to a mobile truck unit. Inspection data is transmitted instantly, allowing qualified operators to interpret and grade welds in real time using digital measurement tools. Compared to conventional methods, RTR dramatically reduces inspection time, maintains production flow, and significantly lowers non-destructive testing costs, especially when combined with automated ultrasonic testing.